In this video, we're going to consider a Schur system where each of the individuals in our system actually has the same independent variables. So remember, we were able to write down our Schur system in a compact form that y was equal to x times beta plus u, where we sort of remember that the matrix X actually represents a diagonal matrix where each of the sort of elements along our diagonal is actually a matrix. And in the situation where each of the individuals has different independent variables, they represent different matrices. But in the circumstance where each of them, or each of the individuals in our system, actually has the same right-hand side variables, each of these matrices along the diagonal is actually going to be the same. So we can write the first matrix along the diagonal is just, let's call it x bar, and then the second one would be x bar, and then we continue all the way up to the nth individual where we'd have x bar as well. And just like before, as we always assume with Schur systems, that each of the off-diagonal elements are equal to 0. Okay, in this video we're going to see that in the circumstance where each of the individuals in our sample has the same right-hand side variables, they have the same independent variables, that in this circumstance Schur estimations, in other words GLS estimation, actually reduces to standard OLS. So there's actually no need to estimate a Schur system in the circumstance where each of the individuals in your sample actually has the same right-hand side variables. Okay, so let's rewrite this matrix X. I hope you can see that essentially because this matrix has these matrices along its diagonal, it's going to have n of these matrices because we're talking about n individuals. So we can rewrite our matrix X as the Kronecker product of the identity matrix with dimensions n by n with the matrix x bar. And to see that, essentially you need to think about an n by n identity matrix, and with each of the ones replaced now with the matrix x bar. And this matrix x bar has dimensions t by t, such that when I take this Kronecker product, the overall result has dimensions nt by nt, which is what we expect. Okay, so why have I done this? Well, it's going to become much easier to think about the Schur estimator in terms of Kronecker delta products. So let's just remind ourselves of the explicit form for the Schur estimator. We know that beta hat Schur is equal to x primed times the inverse of the variance-covariance matrix, sigma, times x, all inverted, times x primed times the inverse of the matrix sigma times y. And also remember that we could actually write the matrix sigma, or originally we defined it this way, as being the Kronecker product of the matrix omega with the identity matrix with t by t dimensions. So what we're going to do in this derivation, or in this kind of proof, is we're going to work away at both sides of this sort of expression. We're going to work first of all on this sort of thing which I've underlined in yellow, and then we're going to work on this term within the parenthesis. And then when we put it all together at the end, hopefully something quite nice comes out. Okay, so first of all, let's think about x primed, because that's the sort of first part of the product which we're considering. So if we think about x primed, we know that x primed is essentially the identity matrix with dimensions n by n, or the Kronecker product of that with the matrix x bar, all transposed. And we know from our rule about taking the transpose of Kronecker delta product that this is just equivalent to the transposes, or the Kronecker delta product of the respective transposes. But for the identity matrix, it's a symmetric matrix, so the transpose is just equal to the identity matrix. And hence, x prime just becomes the Kronecker delta product of in with x bar primed. Okay, and then we can think about the inverse of sigma, because that's the next thing in the product which we're considering. Well, the inverse of sigma is just the same thing as the inverse of the Kronecker delta product of omega with it. And we know from our rules about inverses of matrices, or inverses of Kronecker delta products, that this is equivalent to the inverse of omega or the Kronecker delta product of the inverse of omega with the inverse of the identity matrix with t by t dimensions. But thankfully the identity matrix actually, or the inverse of the identity matrix, is just the identity matrix, so that all stays relatively simple. And in the next video we're going to see what happens when we combine x primed with the inverse of sigma, and then we're going to start working away at this term inside the parenthesis here.